Hello, Pamela.
Hey Fraser, how are you doing?
Wrong output on the audio. Hold on. Now I can hear you. Someday, I'll get this right the first time. And on that day, it'll make us a professional podcast.
Yeah, something like that.
Something like that. Cool. How's it going?
It's going okay. It's brutally cold here, and to record and make sure that the audio was good, I turned off my space heater and got a sweater.
You're right. You did change from our pre-talking to now.
Yeah, I had the moment of oh, that's making noise. Oh dear. Okay, I shall freeze while recording and go
Yeah.
find the thickest, heaviest, ugliest sweater I own.
Yeah, but have you gotten Snowmageddon? Because apparently they got like a pile of snow just in Chicago.
No, we got dusting and lots of wind, and our front trees spewed prickly balls everywhere.
I want to say hello to a bunch of people who are using the Q&A app because that's how you ask us questions and that's how you interact with us here on the show. So I'm going to say hi to Guido Bibra, Nancy Graziano, Jim Meeker, Giselle Sabarin, Sev Dustbunny, Tony Lynch, Matthew Helzer, James Boston, Peter Waldman, Todd Howard, Thomas Traniker. Wow, gang's all here.
Everyone's
Yeah,
there.
this is awesome. So say hi when you first join us, put it in the Q&A app, and I'll say hello to you, and then you can, I don't know, use that for your answering machine or something. Fraser Cain, saying your name. Could there be a greater gift?
I'm sure there could be.
Yep, you said in your classic Pamela Gay style. Cool. So if you have no idea what it is you've stumbled into, this is a live recording of our weekly Astronomy Cast podcast. So we'll take about 28 minutes to record. I don't know why it's 28 minutes. That's how long it
It's
goes
what
for.
you landed on.
Yeah. I like to be just shy of 30 minutes. So, yeah, so around that. Sometimes we're a little longer, sometimes a little shorter. Anyway, so we'll take about that long to record our show, and then we'll stick around and we'll answer your questions about space and astronomy. Not just about the topics we talk about in the show, but really anything that strikes your fancy. And this is the way. And just sort of let people know, you know, we mentioned this last week, but, you know, we get a ton of questions. Pamela gets a zillion questions every week by email. I get a zillion questions. Astronomy Cast gets a zillion questions, and that's just by email, and then they all come by Twitter, and they all come on our Facebook post. So I want to somehow just encourage you all that the best place to get your questions answered is to post them into the show, ideally live. So just, you know, by all means use the Q&A app and we'll get your question. But also just post your question into the event page each week for Astronomy Cast. And then I will go through that list, and because not a lot of people post questions to there, you have a really good chance of having your question answered. Because we get like I don't know, we get these huge emails where someone lays out this really complicated, you know, question, and we just don't have time to answer it in any other
Yeah,
way. So this is the place, right here, Astronomy Cast, live. Let's do it. All right. Are you ready to record?
I think so. I hope so. I'm pressing record once I find the button. I have way too many windows open today. I am pressing
You pressed record.
record.
Okay, you just froze up for a second as you pressed
There.
record.
Yeah, no, it everything on my computer froze, and then it unfroze, and I'm fine now. Hi,
Okay,
Preston.
good. Hello, Preston. All right. Let's get cracking.
Okay.
Astronomy Cast, episode 366, Finding Planets with HARPS. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I am doing great, and I just want to give people another reminder, if you are listening to the audio version of this podcast, and if you've got some compelling question about space and astronomy, we would love to answer it. However, you've got to do us a solid, which is that you've got to go and take that question and put it into the event page for the next recording of Astronomy Cast. So instead of sending us an email, just go to the Astronomy Cast page on Google+, find our next show, and just put your question in there. And we will be glad to answer it live. And not only that, I'll take your question and I'll crank it up 3 notches and make it even harder for Pamela. That is how much we want to answer your questions.
And how much he hates me, with love.
Yeah. Because it's hilarious when we make the questions harder. Because so many people send us questions by email, and we just can't deal with them that way. And why answer a question for one person when we can answer the question for everybody all at the same time? So, and then if you want to see your questions get answered right now, unless we come up with a new plan, we should release them on a podcast feed again. Anyway, you can get it from the Astronomy Cast video on our YouTube channel. So let's get cracking with today's show. Here we go. So almost all the planet hunting has been done from space, but there's a new instrument installed on the European Southern Observatory's 3.6-meter telescope called the High Accuracy Radial Velocity Planet Searcher, or HARPS, which has already turned up 130 planets. So is this the future, searching for planets from the ground? So yeah, this instrument's actually been rolling for quite a while. I said it was just installed, but actually it's been cranking since, what, 2003? 2004, yeah. So we're close to a decade of ground-based planet hunting with the HARPS instrument. But let's go back then and explore a bit of the history of just the way we search for planets right now, ground and space, and then talk about why the HARPS is such a great idea.
So we actually started this way. Everything's coming full circle, as it seems to always do. The first planets that were found orbiting other stars were found actually around pulsars using pulsar timing delays, but those are oddballs that we're just going to ignore for the time being, so we know they exist. We acknowledge that. You do not need to send us email.
We get it. Those were the first planets discovered around pulsars.
Yes. But then the first people trying to find normal everyday planets around stars that were potentially capable of supporting life in solar systems and planets as we know them versus planets that have been shredded in the formation of a pulsar. These were found using high-resolution spectrographs and looking at sun-like stars that were fairly nearby. This work was done at Keck, it was done at the 107-inch at McDonald Observatory, it was done at a variety of different places, and it was always done using a high-resolution spectrograph, looking at a bright star, spreading the light out as much as possible, and comparing how those lines slowly drifted in velocity as compared to a cell of gas located in the spectrograph as a comparison source.
Right, and so we're looking for, in this case, the astronomers are looking for the backwards and forwards velocity of the star caused by the gravitational interactions of a planet.
And initially, we're only finding really big planets snuggled up closer to their stars than Mercury is snuggled up to our sun. And this was because we needed to have really big stars, really regular stars that were getting yanked around by really big planets. The bigger the planet, the closer the planet, both of these factors cause more movement in the star as the two objects gravitationally move around their center of mass.
Right, and these are the hot Jupiters that turned up as a complete and total surprise.
Right, and this is where 51 Pegasus was the first one, and we just kept going from there. Now, the problem with this technique is, first of all, spectroscopy is a bear. It requires so much careful calibration to make sure nothing in your system is moving, nothing in your system is flexing, and the data reduction process is not an easy one. It's just hard. It's way harder than looking for your transit, which also requires very careful calibration. Right.
But we've seen we're all quite familiar with, I think, what a spectrograph looks like. It looks like a rainbow with black lines in it. But I don't know if people are really understand where that picture comes from. Like what instrument, what is producing this rainbow, and how are astronomers seeing this rainbow?
So there's a couple of different ways that you can end up creating this rainbow. The most straightforward and simple way that you can actually recreate at home is you have a prism, some sort of a piece of cut glass or a similar cut solid material light goes through, and different colors of light get bent different amounts as they go from the air to through this medium, this glass or whatever it is. Red gets bent one direction, blue gets bent a different amount, admittedly in the same direction. But with this bending, all of the light gets spread out. And then as it passes back into the air, you then send it on its way to the detector. In some cases, you use multiple mirrors. You end up folding the light up in different ways, all of this to get it precisely focused on your detector.
And so really a spectrograph is a prism breaking up the light from a star as wide as they possibly can.
Exactly. And prisms are actually kind of a pain in the everything to use because they're big, they're bulky, you have to rotate them just right. And one way that we've worked to get away from using prisms, which can crack and get all sorts of issues, is we've moved to using what are called grisms. These are finely striated pieces of material that it's the striations on them that, a lot like the surface of a CD or DVD, will reflect the light out into a rainbow. You can actually reflect sunlight off of a CD and end up with rainbows on your wall, or reflect a laser beam off of it and you'll see a diffraction pattern on the wall.
And just do your own spectroscopy at home.
Exactly. It's not quite as precise because it's not like music creates a perfectly repeatable grism, but you can still get a sense of what's happening. With most major instruments, including HARPS, what you're looking at is you have some sort of a grism that spreads all of the light out. But the spreading of light out means you actually need often a room in the basement beneath the telescope. So for low-resolution spectroscopy, some medium-resolution spectroscopy, you just send the light down the telescope like you normally would, and somewhere between the big mirror on the telescope and your camera, you spread the light out into that rainbow.
And so is it literally there's like some dark room somewhere where they've got this great big prism that's being reflected on the wall and a CCD that's somehow picking up chunks of it? Or
it's not. That would be so much more fascinating. No, actually, so for the highest res spectroscopes, you take all of the light and you focus it into a fiber optic fiber, and you send it down into the basement, usually beneath the telescope, nice, cool, temperature-controlled room, and there you bounce it around in a way you cannot perceive with your eyeball because you're taking the light from a star and you're spreading it out over a large area. So even for really, really bright stars, you have to catch those photons for a lot longer than your eye would be catching them. So
right.
We do
You
that
have
with
a lot of photons. Yeah.
But so they spread them out all over Kingdom Come, basically in this room, mirror to mirror to mirror to mirror, lens to lens, grisms involved, prisms involved in some cases. These are very complex optical systems with dozens or more optical pieces quite often.
Cool. Okay. So this is the Planet Hunter's toolbox.
Yes.
And this has been done from Earth. This has been done from space?
Not so much, just because if you're going to take up an entire basement on the planet Earth to do this, it's not like the Hubble Space Telescope has a basement beneath the telescope that you can put your spectrograph in. So when we're doing the high resolution, looking for planets using Doppler shift, we're doing this from the ground.
Right. Okay. And so then, of course, the space-based method, a lot of it is, like, thanks to Kepler, is this transit method. And this is just this other way of finding planets. So I think this gives people a pretty good understanding of what the spectrograph is, how it works, and this is important because, this is what the HARPS instrument is. So let's talk a bit about the actual HARPS instrument and sort of where that came from.
Right. So the smaller the planet, the less its gravity, the mutual gravity between it and the star causes the star to perceptively move. When we first started looking for planets orbiting other stars using this Doppler shift, looking for the planets to mutually cause the star to go away from us as it orbited the system center of mass, come towards it towards us, towards the spectrograph, as it orbited the system's center of mass. Originally, we were looking for multiple meters per second kinds of motion. So imagine someone sprinting. The velocity of a human being sprinting was what we were expecting the stars to be doing in order for them to be detected here on the planet Earth. We would do a series of measurements, a whole bunch of stars would be involved, spectra, 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 go back later, spectra, 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 take repeated motions and build up a light curve, except it's not a light curve in terms of changes in brightness, but rather changes in velocity. So you look for the star's velocity to be 0 as it's to the left or right in the plane of the sky of that center of mass, to moving straight, as it's directly in front of the center of mass, directly behind the center of mass, to being moving straight towards us, which is when it's either to the left or the right, depending on the orientation of the orbit. So you'd see this velocity change from moving towards us, moving away from us, not moving. Build that curve up over time. See it repeat over time. Look to see, are there spectral lines from another star in the system? Is this a binary instead of a planet that's causing this? Make sure that all the lines in the star are moving, because if what you see instead, you have to worry about different chemical effects. This really doesn't play too big of a role, but you still just double check everything's moving. With transits, you always have the fear, well, this is actually the star pulsating. So what I'm seeing is some sort of an astroseismology, some sort of an internal dynamics of the star. When you're looking at spectral lines, you don't generally see one of them moving just because it can. You see all of them moving just because all of them are getting yanked around with the star, but you still want to check. Just, is there anything weird going on? Do you see changes in chemical composition? That would be awesome, because that would be a paper all by itself. But it's a complicated process. I'm blathering.
Yeah, well, now let's get on to the question that I asked you, which was sort of how the HARPS instrument, where did it come from and what is it?
So HARPS came from the European Southern Observatory. It was built via a consortium and put down on the 3.6 meter at Le Cille. So this is down in Chile. This is another one of those South American telescopes in amazingly dry, high altitude locations. And 3.6 meters isn't all of that grand of a telescope now that we live in this generation of 8-meter behemoths, but it's big enough to catch. You're starting to be able to do spectral work on fairly small-sized stars, which is actually important to what they're doing. And with the HARPS spectrograph, this is an Echelle spectrograph, which basically means it folds the light up really nicely. Fiber optic system. With this particular system, they're able to start measuring walking speeds in stars. So if you can imagine jogging through space, you can outpace the movement of the star, because they're looking at, well, basically 1 meter per second with effective precision down to, once everything is calibrated and everything else, down to 30 centimeters per second kind of motion.
Wow. And so what is the capability then? I mean, this is the motion, but what does that really let them discover?
Well, for looking at small stars, it allows them to start finding super-Earths around stars smaller than our sun. So HARPS is actually how the smallest planets have so far been found.
Just think about that, folks. Right? This is the instrument that's found a lot of the smallest ones that we've seen. And do they typically have a name that people would recognize when they hear them?
See, that's the problem, is they're going through and they're looking at known stars, cataloged stars. So they're looking at things out of the Henry Draper catalog. So it's like HD 10180, and then you'll see A, B, C, D, E, F. In that particular system goes all the way up to the letter H as you go through the planets. So you're looking at things that have these existing catalog numbers that just happen to have planets, and
right, the Galiza catalog, and,
right,
yeah.
But to point out things that this system has done that people have probably heard about. HARPS is the system that confirmed back in October of 2012 that Alpha Centauri b actually had a planet. So this is where you get to Alpha Centauri BB.
Once again, folks, there's a planet at Alpha Centauri b.
Yeah.
Closest, one of the closest stars to the sun. They found a planet there.
And this is all made possible looking at the Doppler shifts. And what's cool about the Doppler shifts is, unlike what's happening with Kepler, it's not as reliant on very, very precise alignments. So when you're looking for a planet to cross in front of its star, it either has to be snuggled up very close to the star, so it has a high probability of crossing in front of that star's face, or it has to be very precisely aligned so that its orbit just happens to nick across that star. That really limits what systems you're able to see. Well, with HARPS, well, yes, they are doing a lot of follow-up on potential planetary systems that have been initially identified looking at transits. They can also go through and look at these nearby stars, like Alpha Centauri, that we know don't have transits, and say, hey, we can see all of these other alignments where the planets are yanking around the star but never crossing in front of them.
Right, and I can kind of imagine the situation, right? I'm thinking about my engineering background now, and I'm thinking about sort of the way we used to calculate various vectors and stresses on things, right? So in this case, you can imagine, if the star was or the planet was directly in front of the star, very close to us, and it was pulling back and forth, you could see that star really moving back and forth as the planet was going around it. But if it's at an angle, it still has part of its velocity that's moving, I guess, up, and part of its velocity is moving away from us because it's actually moving up and down at an angle, right? And so with a really sensitive instrument, if you can calculate, if you can catch that 30 centimeter per second motion, it might actually be moving 10 meters per second almost up and down, but the fact is, because you're getting that little bit of motion that's going backwards and forwards from our perspective, you're going to see that in the star. And so it really just gives you a much wider range of stars. Theoretically, you could pretty much use that to find anything that's not face on, right?
And what's really amazing about stuff like this is with transits, you can sort of get at we think that there's multiple planets in this system based on the oddball periodicity of the orbiting planets, where there's clearly effects of a secondary body that is yanking on it and changing the timing. But with the Doppler shift, it actually starts to become much more, once you've reduced all the data, it becomes much more readily apparent that, hey, the system has planets B, C, D, E, F, G, and H all lined up, all affecting the central star in highly repeatable ways that they can detangle with instruments like HARPS.
So HARPS is able to find the super Earths going around some of the smaller stars, right, like around the red dwarf stars. And I know that one of the big concerns for a while was, so what? Red dwarfs are awful, awful places to live around, so you don't hope for life. But that's not even necessarily sort of true anymore.
Well, it's complicated as so many different things are. So if you have a planet around a red dwarf, what you have to worry about is when that red dwarf star is very young, it is an evil, nasty little X-ray flaring monster that is going to irradiate its entire solar system, and that's just not pleasant to be around. And you also have to worry about, depending on where you are within that habitable zone, are you tidally locked to the star, which can lead to all sorts of weird convective cells and massive winds and all sorts of issues like that. But the more we think about what does it take to get liquid water, the more that we learn about our own solar system, it's possible that one of those planets that got completely irradiated early on had water and potentially other organic materials come to it later on via comets, via asteroids, via a variety of different means. It's possible that you have things that are heated through binary planets that allow you to be further out so you're not tidally locked, but still capable of supporting life. There's so many different ways to get that liquid solvent, which is what water is. There's so many different ways to get enough thermodynamic heat transfer to allow chemical reactions, which is what we rely on geothermal vents in the sun for. There's more than one way to get at those things that are required for life.
Yeah, I mean, one of the things that's quite interesting is the mystery of hot Jupiters, right? How do you get an object that close to the star? And so there's
without falling in, getting
without
them
falling in,
getting there and staying there is hard.
Yeah. And so it's one of these ideas that maybe there's migration going on, and so you could have the planets out further in the solar system and then the migration. And there's an interesting piece of research that actually just came out this week, and I'm not sure if you're even aware of this, but people have done some research that actually mini Neptune-sized worlds can have their outer atmosphere irradiated away by the star such that it ends up being a super Earth when that process is done.
That would explain a lot of the planets that have had us confused lately.
Yeah, exactly.
So that's good work.
Yeah, and so that's one explanation for why you've got these super Earths around these red dwarf stars, is because they used to be more ice giants and they just had the outer layers blasted off. You would end up with one being tidally locked. So anyway, that's the thing. We've talked about the limits of where these telescopes can go. Now I want to talk about the sort of the future because it feels like, with things like the Very Large Telescope, and then the overwhelmingly large telescope, the extremely large telescope.
It's all a matter of what instrumentation they put on these telescopes. And here, actually, with the VLT, the Very Large Telescope, which is an existing system of multiple, I believe it's 8-meter telescopes. They are in the process of commissioning an instrument called Espresso, and it's spelled ES, and it stands for the HARPS Spectrograph for Rocky Exoplanet and Stable Spectroscopic Observations. And this is something that would potentially be capable, if all goes well and above spec, and I mean that's the thing, is they're always looking for things to be a little bit better than spec. It would be able to detect planets like Earth around suns like our sun. The Earth exerts a 9 centimeters per second movement on the sun.
Yeah, crawling speed.
Crawling speed. And so if you can imagine a very anxious toddler chasing down the sun, that's a possibility. And Espresso is potentially going to have the ability to do this. Its requirement is 10 centimeters per second. It's felt that they'll actually probably be able to obtain better than that, but the requirement on delivery is 10 centimeters per second. And because this is attached to so much larger of a telescope, 8 meters, it's going to be able to look at fainter stars for smaller planets and more distant stars that are brighter. So you have something that's or more luminous. So you have bigger stars at greater distances, nearby stars that we couldn't look at before because they're too faint. We're extending the types of stars we can look at and the bubble of space that we're able to explore. And so this is a very exciting instrument that is nearing completion, and I'm just like itching for it to start joining in the discovery. And so between the original HARPS, we also now have HARPS North, which is an identical instrument that is in the Canary Islands, and this upcoming Espresso, we're starting to get so much better at zooming in on the characteristics of the stars that have planets, the variety of planets. You combine all of this information with the Gaia mission that's going to give us the very precise astrometry motions. So now you have very precise in and out of the plane of the sky motion from HARPS and Espresso. You have very precise left, right, up, down in the plane of the sky motion from Gaia. We're getting at amazing information on how the stars are moving under the influence of planets.
And there's one, I guess, I mean, as you mentioned, right? It's amazing. It's all coming together. You've got transits. You've got the astrometry astrometry that you can see it side to side. You've got the radial, the Doppler method, so you can see how it's moving forward and back. The last piece of the puzzle is coronagraphs, right?
Not working on that right now so much.
Not yet, but this is the thing where you block out the light from the star and you can actually see the planets and start to image these things directly. And I think you put next week we're going to be talking about finding planets with Spitzer, right?
Yes.
And so this is part of the job of actually imaging these planets directly, because this is something that Spitzer has done.
Yes.
And so next week I think we're going to go deep into both the work that Hubble and Spitzer have done to image these planets directly and the future of what that looks like.
And what I really love about this theme is it really requires people on the ground, spacecrafts in space, instruments everywhere, all working together to build a complete picture. And there's really room even for people out on their driveway with their 4-inch telescope.
Are we going to have our terrestrial planet finder after all?
No.
All we just had to do was just wait for a whole bunch of separate instruments and telescopes to all be built
it's
together, like
what it was capable of doing. No, we're not going to get there. We're getting to a different future.
Yeah, well, it is a different future, and I'm almost about to say that it might be a better one. Instead of one monolithic observatory that does everything, you've got a whole series of incremental improvements across a bunch of different instruments and spacecraft that's going to get us to the place of being able to find that holy grail, right? Yeah. Being able to smell the atmospheres of other worlds. Yes. That's what we need to do. Cool. All right. Well, thanks a lot, Pamela, and we'll continue this conversation next week.
Sounds great.
All right.
And I really don't want to actually smell an atmosphere. Have you been through Gary, Indiana?
No.
Don't.
Okay. Is that a particularly smelly atmosphere?
Yeah, it is. There's like certain places in the U.S. where on road trips you make sure your windows are up and the air intake is not from outside. Beaumont, Texas, and Gary, Indiana are two of those places.
I've been through Beaumont, Texas many times.
Okay, so you understand.
I do, yeah. Okay. Just going to upload this thing. Yeah, I can't believe I'm going to say this, but I'm pretty excited at at how many technologies are coming online to find planets, all different methods, all the systems. Yeah. It's pretty great.
Yeah, it's pretty awesome.
Okay. It was funny. I did a interview with someone. I don't know if the article ever came out, but someone was wanted to talk about how sad and depressing the space programs are and how we're not really exploring space anymore. And I just are you crazy? like all of these instruments, all of these telescopes, all of these robotic missions, all of heavy lift systems.
It's a mixed
so much
bag.
Stuff going on right now.
I keep looking over at my Twitter feed because folks are seeing new NASA budget numbers come out, and the current budget for 2016 for Mars rover and Lunar Reconnaissance Orbiter are both 0. And so there are certain sub-areas of science, like the moon, apparently, where you just sort of oh, that hurts. And so big picture, we're still in a golden era, although we're slowly falling out of the peak. But when you look at certain sub-areas, especially in our own solar system science, there are moments of great depression.
Oh, I know. As someone who gets a lot of her budget from that world, I know it's smarts. All right, let's take some questions here. Richard Summers says, first time here, excited to be present for the live program, about 12 inches of snow in Syracuse. So there you go.
I want that amount of snow. I don't want 36 inches. I want 12. Ship it to St. Louis.
Steve Chisel asks, on the topic of mounting heavier instruments like spectrographs, is that easier to do if the scope has a azimuth focus?
No, you just need a basement and a fiber.
Right. So it's really about getting that light out of the telescope and then into some big place where you can process it with lots of bouncy prisms and stuff.
And they run the fibers off of, so with HARPS, they run the fibers off of the Cassegrain focus. With telescopes like the Hubble telescope, they run it off of the primary focus at the top of the telescope. I've used telescopes that use a coude focus, which comes out the side of the telescope. So you can run a fiber anywhere you can focus light.
Nancy Graziano asks, so once we move beyond low Earth orbit, say to Mars, or even back to the Moon, will there be any significant advantages gained over ground-based observations using systems such as HARPS? So,
with the Moon, you actually have some really nice advantages, but it may not actually be a sufficient advantage for optical astronomy to do it there. So with radio astronomy, you don't care about sunlight, so the fact that day is like 15 days long isn't really an issue in the radio. But the thing with optical and radio telescopes is both of them flex, which means that as the telescope gets further and further away from the zenith, you run into problems with your entire optical assembly bending slightly. Focus will change. It's a whole myriad of different problems, and what you end up doing is building complex mount models that take into account pointing changes and focus changes as you move away from zenith. With the Moon, gravity is a whole lot less, so you clearly don't have these problems with flexure. You also don't run into the atmospheric aberrations. There's so many different things. If you build on the back side of the Moon, not the dark side, the back side of the Moon, you don't have, for radio astronomy, problems with radio pollution from clearly the Earth. So there's lots of advantages, but with optical astronomy, dust on the Moon is a never-ending problem that we still haven't fully figured out how we're going to mitigate, and getting dust onto optical instruments is death.
But I guess, like, is a spectrograph a good instrument to run from Earth, because you don't necessarily need the resolution, right, that you might with and I could just be making stuff up here, but like, I know one of the problems with putting a telescope on Earth is that it has to go through the Earth's atmosphere, and you get the aberrations of the atmosphere.
Yeah, you can actually unfocus the telescope slightly when it comes to the point spread, but then you have to have, once the light gets in, you have to have it very precisely focused, so the spectral lines are in focus.
Right, so you're not going to get, like, the variations of the atmosphere isn't going to change the energy of the photons too much, is it?
Right.
Okay, yeah, so spectrographs just are more usable in the Earth's atmosphere than necessarily something like where Hubble, when what you really need is that the ability to focus in really tight and resolve, the resolution of the telescope. That's when you want to be out in space.
Well, and there are some interesting phase issues that we're still trying to understand, because telescopes like the Very Large Telescope can actually get resolutions like Hubble's from the ground, but the issue starts to become, is all of the light precisely in phase when it hits the detector? And that starts to get into a very complex argument well beyond the scope of anything short of a full episode.
Right, and we've sort of done that, but yeah.
Yeah.
Okay, cool. Let's see if I can grab another one here. So Guido Bibra asks, Steve Chisel mentioned Slacker Astronomy. Are the old episodes with Pamela available somewhere?
I actually went looking for them and couldn't find them. Yeah, it's really frustrating. I'm hoping that there's someone out there who might be hearing this right now and say, hey, I have all of them on hard drive. If you do, I have a Dropbox I'd love you to drop them into.
So there is a Slacker Astronomy website, but they only go back so far?
They actually only go back to... So the Slacker Astronomy podcast went through multiple evolutions. There was the original show that ran 2005 to 2006. It ran for a year and a half, where everything was scripted and hokey, and we had a blast. And then it went through a phase change, actually changed a lot of the cast members. That was when you and I started Astronomy Cast, and I started my job here at SIUE. And that phase change is also not online. And then it changed hands again and ended up being just Michael Kopelman and other random individuals having fun online. Some of those episodes are still online, but again, it's only the most recent ones. So.
And this is a problem, right? That's a larger problem of just us living in the internet age, is that our media, like, it will disappear.
Yeah.
Right? History is disappearing. So you started Slacker Astronomy, then moved to Astronomy Cast, and because I'm so concerned about this, I am a total
Our stuff's all on archive.
Yeah, I'm an archivist, and I've got it. We've put everything on archive.org. We've made it as available as we can, and I really obsess about making sure that the stuff is going to be around as long as possible.
Yeah, we've been very careful with it.
And this is something that I've been quite nervous about, and I even wrote a letter to the Canadian government, like literally 15 years ago, saying, "Hey, because of the internet, we're going to be destroying our history. So we should do something about this." And nobody ever got back to me. So, so in my own little corner of the world, I really try to be obsessive compulsive about us doing it. Hey, Steve Chisel saying, I don't have a lot of them, but I don't have all of them, but I have a lot of the Slacker Astronomy podcasts on my
that would be awesome.
Yeah. So if you could just send Pamela an email.
Yeah.
starstrider@gmail.com. That would be awesome. Yeah, so anyway, there you go. History is deleting itself. We only live in the moment. We're all.
Thing is, it's such a catch-22 because all the things that matter that we used to keep in printout form are disappearing because we thought they'd be safe on hard drives, on disks, on the cloud. But then how often have arguments resulted in people digging out emails and texts that otherwise would have been ephemeral?
Mm-hmm.
So we have completely broken the communications system.
Yeah, and so people 100 years from now, 1,000 years from now, aren't going to be able to dig through or look in old libraries or dig through our garbage to find this old data. It's going to be gone. It's all going to be electronic, and it's up to the individuals to decide whether or not they're going to hang on to it or not. Right. So all hail the folks at archive.org because they're doing really special work, I think. And in the future, it's going to be remembered as one of the most important projects that has been done on the internet. So
things you should donate to.
Things you should donate to, exactly. David McKee asks, how do we know about the 9 centimeters per second measurement of the Earth that you're talking about? How is this measurement taken? So how do we know that the Earth moves the sun 9 centimeters per second?
You can actually get at it mathematically looking at it's a combination of you look at how all the other planets are getting offset, you get at the masses of things that have moons, you get at the masses of things that have had things fly past them. That's how you get at Mercury and Venus.
But isn't it just a calculation? Like just calculate the barycenter of the Earth and the Earth and the Sun, and then
with just the Earth and the Sun, it's also I'm telling you how to get at all the motions of the Sun. Yeah, you take the mass of the Earth, you take the mass of the Sun, you do math. And you get it at 9 centimeters a second.
And then, you do the math to determine where it is, and then you just calculate how long it, over the course of the year for it to shift between those two positions, and that tells you its velocity.
And honestly, it's a freshman physics problem. It's not that hard.
There you go. You've been assigned. Calculate the shift. All right. Let's see what else we got here. So Steve Chisel also says, building on the earlier question about scopes, I noticed that you gave the Schmidt-Cassegrains a passing mention in a few of your other episodes about telescopes. Matsutov Cassegrains are conspicuously absent. Why? They're rugged, compact, sharp, and expensive.
Well, so first of all, Schmidt-Cass is much easier and much cheaper to produce. And for most scientific grade telescopes, you're either looking for the really large field of view that you get with a Schmidt telescope, or you're looking for the very flat across the entire field of view field that you get with a oh man, I hate this. I just totally forgot the type of telescope I've used most of my life. It's one of the French names. It's gone.
Richie Chrétien?
That's the one, yes. So you're looking at either using a Schmidt type or a Richie-Chrétien type. Cassegrain refers to where the light pops out. So you have Cassegrain focus, Coude focus, and you can get at those focuses with multiple different types of mirrors.
Right. Okay, so Elad Avron says, so right now we're using a lot of inference to discover planets. Are there any upcoming technologies that will allow us to actually see and examine those planets? And so
we can see them with Spitzer, so we'll be talking about that next episode.
So we'll definitely, and of course I will speculate wildly. So or I will encourage Pamela to speculate wildly. So
which I don't do.
Which we'll definitely be talking about those future technologies, especially coronagraphs. I
can see what you're obsessed upon.
I am totally obsessed about coronagraphs. There was just this week. Oh man, Webster Cash from University of Arizona just released new plans for his next version of the telescope that will be 1,000 times more powerful than Hubble.
Cool.
Yeah.
The folks down in Arizona do amazing designs.
Yeah. Okay, let me see here.
So I see that Guido Bibra is saying first Astronomy Cast in February, and so it's Groundhog Day, which I know because two of the comics that I read had very bizarre, off-color, ground-up hot dog ads. But on Twitter, I just retweeted this. There's a picture of a groundhog, like totally chomping down on the ear of a mayor who's like holding up the groundhog for Groundhog Day. I don't know why that delighted me so much, other than we have pet groundhogs in our yard that came with the house. So.
Right. Did they see their shadow?
They're hibernating quite happily. So.
Yeah. No. So then it looks like I forget how this works. It's the opposite, right? If they don't see their shadow, then winter is going to be short. I think. Anyway.
I have no idea. George is still asleep. That's all I know.
Ed Thompson says, hello, Pamela Fraser. I don't have a question as much as a thank you. I once asked your advice on getting a telescope, and your insight really helped me pick a telescope that I use very often and get the results that I was looking for. Thank you. Well, that's awesome. We get, like, if there's literally a question that we have had a lot, it's recommending a telescope. I think there should be, hear me out, a Dr. Pamela Gay telescope, branded telescope. It's the one that you recommend, the one that you like, the one that's, that's whatever, easy to set up.
I'd happily work with the manufacturer on that.
Do you hear that, manufacturers? This is your chance. Okay. Let's see. All right, let me see. I'm going to pull some questions from the comments.
I'm not seeing anything. Really?
Really? Oh. No, okay, here we go. So Charles Wagner says, with all the new planets we've found, have the theories around planet system formation changed?
Say that again. Sorry, Twitter.
So Twitter rots your brain.
Yes,
so with all this comes from Charles Wagner. With all the new planets we found, have the theories about planet system formation changed?
Yeah, we don't know how they form. I mean, we know big picture, solar nebula. How they get where they are, the stuff things. Still working on it.
I mean, even just this year, there's, one of the big questions is how you can get from microscopic, just individual atoms to dust, and is it like is there some kind of electrostatic thing that makes them cling together? Are things being smashed together that they're actually like gluing together through the collisions? What's stopping them from just being exploded again by other collisions?
There's so many open questions. But yeah. I mean, this is the thing about science. We often have big picture understandings of things, and when you start asking details, people have to just start saying, I don't know. I don't know. And often the I don't know stuff isn't sexy. Like convection, don't fully understand it. It's a thing. We know it exists. We know it's in stars. Don't fully get it.
Dark matter, right?
Well, no, that one isn't under the people often assume that it's a solved problem. We teach undergrads about convection. Everyone assumes it's not a solved problem. How dust affects things, magnetic fields, why the Earth has a magnetic field. All of these things, we have big picture, wavy hand things that we use to explain to undergrads, and then we go home and we just sort of like, I don't know really how this works. And it's so frustrating to have this glimmer of insight but not know the details when you really want to know all the things, even though we know if you knew the positions of all of the molecules and the velocities of all of the things, you still couldn't predict anything. But we want all that information. We just can't have it.
Peter Waldman asks, is it planned to put a similar instrument to HARPS into the EELT, and what would that be capable in terms of the lowest massive detectable planet? So, EELT, that's the European Extremely Large Telescope. How big is the EELT? It's extremely large.
Well, so one of the problems that they keep running into is different people join and leave the partnership, and this has caused downgrading in the size of the telescope, downgrading in the instruments of the telescope. So like so many spacecraft, it's on the list of things that I sort of know are on the planning, but am not following closely until they actually like have first light.
40 meters.
But do you believe it will actually be 40 meters when it's completed?
Yes. 2024. So
do you really believe it will be 40 meters when it's
Yes! Yes, I do. I do believe that. No, let's see. So there's the Giant Magellan Telescope is going to be 24.5 meters. The 30-meter telescope will be, I don't know how big the 30-meter telescope is going to be, some amount. And then the ELT is going to be 39 meters. So you've got 30 meter, you've got 24, 30, and 39. So the point being that these are, when you look at the work, bigger than the 8.4, although that is they are mashing the light together.
Well, so the thing that you have to remember is you're dealing with two different problems. The size of the mirror determines how faint an object you can see and how small a arc seconds wide or fractions of an arc second wide separation you can resolve with your single mirror. The spectrograph determines how many centimeters a second you can resolve. So you can do that 9 centimeters a second on the Lassell 3.6 meter if you really want to, but you're not going to be able to see as faint a star. So
right.
We don't know.
A bigger room.
Yeah. So
with more fiber optics and longer time periods that you're gathering those photons for.
And different science outcomes have entirely different purposes. So if your primary science goal is, I want to see as high a resolution velocity change as possible, you build one type of instrument. If you, however, instead want to see as much of a star's composition as possible, you're going to build a spectrograph that may not have as fine a centimeters per second resolution, but can instead see further into the red and further into the blue. So there's a variety of different questions you might want to ask, and each of these questions requires a different kind of instrument. And you're limited in money, you're limited in physical space, and those telescopes aren't built yet.
But can we just agree that more bigger, more better?
No.
Really? If I delivered you a 40-meter telescope, you couldn't think of things to do with it?
I could think of things to do with it, but I'd also be very happy with a nice 1-meter telescope in a dark site that had a giant field of view.
But what about a 40-meter telescope in a dark site with a good field of view?
I then
Which would you choose? Which would you prefer, the 1 meter or the 40 meter? See, we could play this all day.
The problem is I would have to share the 40 meter, but I have a reasonable belief that I am capable of having a personal 1 meter someday.
Adam Synergy says, the HARPS Spectrograph, one of the most important scientific instruments of the past 20 years and possibly of all time. Am I overtaking its importance?
No.
I don't think so.
I'm totally with you. That's why I wanted to do an entire show on this one instrument.
Mm-hmm. Yeah. So there you go. Like, one of the most important, and I know there was a lot of preamble, like we had to sort of really explain the way the science works, and but you know, I think I totally agree. Like many of the planets that you've been excited about came from this instrument. So.
Yeah.
All right, last question, and this is sort of a bigger one. I'm going to try and mush it down a bit. So this comes from Richard Summers, and speculating about, this is just right up your alley, which is about asteroids. Do you think asteroids would be useful as spacecraft for exploring the solar system? So why?
Because they're already up there, you dig a hole into them, you have your radiation protection because you've dug a hole underneath things that will block the radiation. And there's so many different ways. You mine them first, you use what you mined out of them to finish them off as a spacecraft, and now you have an easy body with lots of dirt to protect you from radiation.
Yeah, seal it up, fill it with air, and rotate it, and you've got everything you need.
There's two books that use asteroids really nicely in them. One of them actually does a lot of discussion, and I'm going to have to open up my Audible account to remember the name of it. The other one is Mary Norris Russell's The Sparrow, which is a book that caused me to openly cry in the London Underground because it is that sorrow-causing of a book. But they used an asteroid quite effectively as a spacecraft. The other book series, actually, that uses asteroids and small moons as colony ships throughout it, I'm still hunting through.
But I know that
it's the Leviathan Wake series. So if you start with the Leviathan Wake, Armageddon's Gate, Caliban's War, all of these books are by James Corey. They use hollowed out space rocks throughout the series, and they do it very realistically.
And I know
the rest of the series is not realistic, but that aspect is.
Right. This is one of your favorite ideas for setting up permanent human civilization in space, because there's mountains and mountains, literally, of room in these things. They're already traveling on fairly useful trajectories. Get enough going, and you're going to have, it's going to turn into, like right now everything is so far away, but you get enough of these going with all of their similar and interlocking orbits and all that kind of stuff, and you can imagine traveling from one to the other, making your way around the solar system. So we
need to become space molemen. Spaceborne molemen. That's the future of astronautics.
Yeah, exactly. And the fact that you could rotate them and build and have essentially artificial gravity is huge, because we don't even know if a human being can survive in microgravity for anything longer than
a few years.
Yeah, a few years at most. Clearly the impact, the medical impact on the human body is catastrophic from being in microgravity. And so there needs to be some long-term thing. So you take an asteroid, you spin it up to the point that you've got artificial gravity, you've got radiation protection, and you've got raw resources. Absolutely, it's the best. So
and those are all things that James Corey goes into in his Leviathan Wake series. And one of the interesting things to think about is, if you spin up an asteroid, these are fairly small, so just the act of going up and down one stairwell will change how much you weigh.
Yeah, so you're going to spend time, it's hilarious, you're going to spend time in these asteroids at different gravities to do different kinds of functions, right?
Well, and you can also imagine things like the wealthy travelers get Earth gravity, whereas the more impoverished people suffer the health effects of having room and board in the lower levels, where the lower levels aren't the ones without windows, they're the ones with lower gravity.
Yeah, that's awesome. All right, well, let's wrap this up. So thank you, everybody who asked questions. Thank you, Pamela, as always, for bringing the knowledge. I'm looking forward to next week, because as you can tell, this is one of my sort of favorite concepts in planet hunting. So I can't wait to talk about looking at extrasolar planets, and that'll be next week.
And all you Northern Hemisphere people, stay warm. It's brutal for many of you. And enjoy the snow if you have it. And I'd like it, please.
Awesome. All right. Well, we'll see you all next week.
Bye-bye.